All right, last time we talked about being able to draw ray diagrams, do ray tracing for convex and concave mirrors. And we can kind of see, if I save this one from last time, the image we got was smaller and it wasn't caused by the actual light rays, them converging on the same spot. Um, they're formed by kind of these, kind of extrapolated from the ray tracing that they form this kind of virtual image here. It's not real. It's just kind of what we can see. Um, and we'll talk about the difference between, what you can see and real images later on. Um, the So a couple things to point out. So F, once again, is still the focal point. The equations that we're going to use here, some questions we might be asking is, what is the distance that this image is forming at? How high is the image? What's the magnification of the image being formed here? So I'm even going to label that. That's my image. That's my object. So now we can kind of look at, so the formula we can see that really relates the distance that the object's at, or how far away the object is from the mirror, and the distance that the image is from the mirror. It's 1 over the focal point of the mirror is equal to 1 over distance of the object plus 1, so 1 over distance of the image. That's really the formula we're going to use. It's pretty basic, it's pretty easy. I'm going to bring up a separate calculator quick, and if I can find it, there it is. All right, so starting off with, let's say that I want to know how far away is this image forming from the mirror. So let's just say that the focal point is 10 centimeters. That means the center of curvature then is twice that, 20 centimeters. And we're going to say the object, which is in between, let's say it's even halfway between them. Let's say that the object is 15 centimeters away from the mirror. Now, in order to find out how far away that image is, a couple things about that focal point. It can have a sign, positive or negative. For concave mirrors, your focal point is going to be positive, and for convex mirrors, your focal point is going to be negative. It's kind of it's negative because it's on the opposite side of the mirror the object's on. It is one way you can kind of think about that. And if we're looking at distances of the image, how far away the image is, for real images, your DI is going to be positive because, once again, it's on the same side as the object. And for virtual images, which is the one we're working with here, DI will end up being negative just because it's on the opposite side. You can kind of think, if this is a number line, my positive numbers are this way, my negative numbers are that way. All right, so let's just try to get things set up here. So I said that the F we had was 10 centimeters, but in this case, we're working with a convex mirror. It's bending towards us. So it's actually going to be negative 10 centimeters. The distance of the image is what we're looking for. And the distance of the object, we already said, was 15 centimeters. Keep in mind, the distance of the object is always, always, always positive. It's never going to be negative, because essentially the object can't exist on the other side of the mirror, if that makes sense. So now I'm just going to plug things in. So I've got 1 over F, which was negative 10 centimeters, is equal to 1 over the distance of the object, 15 centimeters, plus 1 over DI, which is what we're looking for, so I'll leave that DI. All right, so the first thing I'm going to do is probably subtract 1 over 15 over. You could figure out what that decimal is. So let's just go 1 over DI is equal to 1 over negative 10 centimeters minus 1 over 15 centimeters. All right. Can you use actually, let's try the Windows calculator. I'm not doing exponents. I don't think I can mess things up too bad here. Yeah, watch me prove that wrong. All right. So let's go 1 divided by negative 10. All right, already messed up. Open parentheses, 1 divided by 10 negative, close parentheses, minus parentheses 1 divided by 15 equals. All right, so over here, I got that to equal negative 0.167. Let's just round it to that. 167. So that's what 1 over the image distance is. In order to get just the image distance, essentially I'm just going to raise this to the -1 exponent. Because that's just going to flip it, like essentially, yeah. That's going to get my di out of the denominator, and yeah, that's just how we solve it. So let's figure out if I can do that. And then raise to the 1 negative, close parentheses, equals -6. All right, so the image distance we got here was -6 centimeters. So that's how far away the image is. And it makes sense. So if my focal point was 10 centimeters, the image distance was less than that. So even if we call that -10, -6 is closer to the mirror than -10. So that makes sense. I got a negative number, and we did form a virtual image since it was where the dotted lines crossed. And I know that the image distance should be negative for virtual images. So that's good to go. That's what I was looking for. From here, we could figure out the magnification of the image. Essentially, what's the difference in how big the image is compared to the object is? When we're looking at magnification, there are two things we can look at for it. We can compare the heights of the images or the distances of those images. In this case, we haven't found the heights yet. Like, even if I told you that our object started with a height of 5 centimeters, we still don't know the height of the image. We don't have any way to really find that yet. So if we wanted to find the magnification of this mirror, we could go through and just plug in the numbers that we've already found. So when we're working with the distances, it's going to be negative the image distance, which is -6. Let's even go -6 centimeters, over the object's distance, which we said was 15 centimeters. Negatives cancel out the negatives, so I've got 6 divided by 15. 6 divided by 15.4. So at this distance, our mirror has a magnification of 0.4 centimeters. Not centimeters, those cancel. So just magnification is just 0.4. Now we could go through, if we really wanted to figure out, put the wrong thing there. If we really wanted to figure out the height of the image, what we could do is we could plug in the 0.4 into the magnification. So we got 0.4 is equal to the height of the image, which is the one piece of information we don't have, over the height of the object, which I just arbitrarily decided was 5 centimeters. Now to get the height of the image by itself, I'm just going to multiply both sides by 5 centimeters, which should give us 2 centimeters. Double check I did that right. 5 times 0.4, 2. All right, so I did my math right in my head. And so the image height, we said this thing is 2 centimeters tall. And that makes sense. You know, when we look at the differences in the images, I forgot to add that in here. -6 centimeters. It was decidedly closer to the mirror. It's decidedly smaller. Yeah, I mean, these equations are very, very straightforward. I would say the hardest part is just realizing, like, if you're solving for the image distance and you subtract the 1 over the object distance over, keep in mind it's 1 over f minus 1 over d. So popping these things in parentheses when you plug it into a calculator tends to be really useful. The cool thing about those equations are going to be the same equations we use when we start talking about convex and concave lenses. The only thing that might change will be what we consider positive and negative for the focal points and the distances. Just because with lenses, we don't have light rays bouncing off the lenses. The light rays are going through the lenses. But we'll talk about that next time. Good luck.